cancel? What did I do here? It's still recording, right? Yeah, recording. I haven't done this in a while. Okay, let's minimize this. Good. So, half-life. And we describe it with a T, and that's a subscript 1/2, and I'll write that down again in a moment. Every radioisotope has a characteristic property called half-life. Half-life is the time taken for half of the original number of radioactive atoms to decay. So, an individual atom can either decay or not decay. It can't just kind of decay. So it either, poof, gives off radiation, or it sits there in an unstable state, ready to give it off. There's really no way to predict when an individual atom will decay. But it's been determined that if you have a large amount of atoms, billions and billions and billions of them, maybe in like 5 grams of a sample, you can predict when half of them will decay. And we call this the half-life. So let's say you had 10 atoms. That's not a lot, but let's just say 10 atoms. And let's say that these atoms have a half-life of 5 minutes. That means after 5 minutes, 5 of those atoms, half of them, will have decayed and turned into another isotope. It doesn't mean that they're gone, but it means that it's turned into some other atom. So every half-life, half of them will decay. Now when you get to 5, you'll run into trouble because you're down to 2.5, right? You can't really do that. That's why we usually talk in bigger numbers. But after another 5 minutes, half of those would be gone. And after another 5 minutes, half of those would be gone. After another 5 minutes, half of those would be gone. All right? Eventually, you'd end up with 1 atom, and you'd have to wait for it to decay. At that point, you couldn't really use half-life anymore because you can't have half an atom decaying. It either decays or it doesn't decay. So we don't normally talk in terms of atoms. We usually talk in terms of grams, a large amount. So let's do some calculations. Click. All right. So I'm going to do this example with you. Then I've got one practice problem for you to do on your own, and we'll take it up. And then that's it. That's the little half-life lesson. It's not a long lesson. Oh, no. Oh, okay. Yep, good. Good. The half-life of AC, which is actinium, right, the beginning of the actinide series, 227, is 22A. And A stands for years. It stands for annum, like annual or anniversary. Okay, so it stands for years. If we start with 250 grams of actinium-227, then determine the mass that is left after. Now, this mass here, 227, is of no use to us. It's not anything we use in a half-life problem. It's just telling us what the mass of the isotope is, 227 atomic mass units. So that just identifies the atom we're looking at. No need to have or use that number. We could have just said actinium if we wanted to. 22 years is very important, all right? 22 years is the half-life. That's the time it takes for half of this substance to give off its radiation and turn into the next isotope. So I'm going to write that down. T half, 22 years. And I'm getting it from that number right there, okay? If we start with 250 grams of actinium-227, then determine the mass after. So that's important. That's the amount we're starting with. And I'm going to call that M0 to represent the mass of the stuff that we have at the beginning or at time 0. M0 is 250 grams. Okay? The other important thing is in the question right here. The question is, how much is left after a time of 22 years? So I'm going to represent that just by T. That's the time that's passed. 22 years. 22 years. And the thing that we want to find is the mass that's left after time T. So what we're looking for is mass at time T. Question mark? That's what we're trying to find. Now, you might think, Mr. Sanders, you're working way too hard to get the answer for this question because I can see exactly what it's going to be. Why do we have to write all this stuff down in such a complicated fashion? If we're dealing with a time T that isn't nice, in other words, it's not a nice multiple of the half-life, then we have to use an equation to do it, and I'm getting you set for the equation that I'm going to give you. How much stuff's going to be left after 22 years? Pause for thinking. Nolan? How did you come up with 125 grams? Yeah. The half-life is 22 years. That's how long it takes for half of the sample to decay. We've waited 22 years, so how much should we have left? Half. Does that make sense? That's what the half-life is. That makes sense. Yes? Excellent. How did we get that? We took 250 grams divided by 2 to get 125 grams. Now that doesn't mean half of the rock has kind of evaporated away and disappeared into nothing. It means that it's turned into other elements, right? If it's it could have turned into one of these or something like that. It just means that half of the actinium that we started with is now not actinium anymore. Okay? All right. What if we now wait for 44 years? How much is left after time T, 44 years? Yep. How did you come up with that? So it's half of the original one, right? Or sorry, half of the 125. 125 grams divided by 2, because we've undergone another half-life. What if I wanted to represent this as an equation with my starting mass instead? What would the equation be if I wanted to use my starting mass in my equation instead of the mass from the previous half-life? What would the equation be? Yep. Ooh, you want to use 0.5 and multiply it by 0.5? Yeah. And then the power of 2? That's beautiful. I think I'm going to cry. That's a great answer. I'm going to write it a little differently, though. That's exactly correct. You've done it nicely. That's perfect. For those of us who are not as mathematically advanced as Paul, 250, and I would just put divided by 2, divided by 2, right? You did 0.5 instead of dividing by 2, right? I liked your use of the exponent. That's awesome. I was going to save this for the next example, but I'm going to do it now. Or 250 divided by 2 to the exponent 2, because I divide it by 2 twice. All right? That's kind of neat. That means this 2 right here in the exponent kind of represents how many half-lives have passed. One half-life, divide by 2. Second half-life, divide by 2 again, or 2 to the exponent 2. And after all this blah, 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 what did we say? 62.5 grams left. Are we okay? Doing good? Not moving too fast here? James, not moving too fast for you? Good? Of course, I'm going to broadcast this on the internet. I won't say what James' last name is, because I'm recording it. 66 years. Mass, oh, didn't like that. Mass at time T. Somebody tell me what my equation is going to look like from my starting point. Let's say I didn't ask you about 22 and 44. I just jumped to 66. What would the equation be if I'm starting with my original 250? What's going to be there? That's my pause for thinking music. I don't know. I could run some Jeopardy. No? No Jeopardy? What do you got? James, what do you got? What's my equation going to be? I want to start from 250. 250. You guys like this 0.5 business, don't you? I refuse to do it. I want to divide. It would be, it's correct. Then what is 66 divided by 22? 3. Nice. Because we underwent 3 half-lives. Okay? All right? This brings me to the development of a general equation. All right? Let's take that number, though. What is that number? 62.5 divided by 2? 31.25? 31.25 grams. Now, we're having problems with significant digits, by the way, folks. We're getting way too many significant digits here, but I'm not going to worry too much about significant digits until we get into the heavy math in the second half of the course, and then I'll start teaching you about how we have to deal with significant digits properly. Okay, let's come up with a general equation. In general, if I want to find the mass at time t, I need to start with my original mass. What symbol did we use for the original mass when I defined everything at the beginning of the question, or at there? I don't have it on my slide, but you guys have it in your note at the top. What did I call the original mass? Yep. Sorry? What? No, it's not even close. Yep. M0. M0, starting mass, divided by 2. Always divide by 2. To some exponent, which I'm going to call n, which n represents the number of half-lives. So now I need a separate little equation to get the number of half-lives. N is equal to, how do I determine the number of half-lives using the symbols that we've been using in these questions? Yep. T over T1 half. All right? And I'll define this for those of us who are taking some notes. That's black and you can't see that at all, so that's terrible. There we go, that's better. This is the number of half-lives. Okay? That's how many half-lives have taken place. So now we're prepared to deal with something that isn't so nice. N is equal to, there's my time, 478. It's 22 years. How many half-lives have passed in 478 years? This is where you need to get your calculators out and actually calculate it and tell me. Yep, Paul, what do you got? 21.7, and that's good enough for our significant digits. Which means the mass at time t will be equal to our mass 0, 250, divided by 2 to the exponent 21.7. And now we need to get acquainted with our calculators. Some of us know how to use our calculators, some of us less. If you're putting 2 to the exponent 21.7, you're probably going to be looking for a button that is either x to the y, all right, or y to the x, okay? So then you're going to be putting in 250 divided by the way, that's the divided by button right there, if you're just wondering. I'm mocking you all completely. Nobody's saying anything. It's like it's 8 o'clock in the morning and you guys are period 1. Nothing. You guys don't ingest nearly enough sugar at lunchtime. My suggestion is more sugar. It'll be more enjoyable of a class. Okay. 250 divided by, then 2 then x to the y, then 21.7, and then you're going to give me the little number that it gives you. Yep, what do you got? 0.7.3, give me one more. 7.39? 34? 34 times 10 to the negative 5 grams. Nice use of your scientific notation. Did your calculator do that itself, or do you know how to switch it to scientific notation? Petrus! I'm going to give Petrus credit online? This is crazy. It can't be the Mr. Petrus from LCVI. Must be a different Mr. Petrus. Okay, anyway. Nice work. For those of you who didn't switch it to scientific notation, what do you got? Read off some zeros for me. Or did you put it in scientific notation? Oh, okay. Four, right? 734. Nice. I will be teaching you how to turn things into scientific notation as we get further along, but that's excellent use of your calculator. Okay. Anybody not get that answer? All right. Go ahead and do that example, and then we'll take it up, and then there's just a little homework problem, and then that's the end of my kind of review on half-life. Don't wait for me to complete that. Go ahead and solve the problem. A can be done using some simple logic. B, you're going to need the equation. On our quiz, I'll tell you that right now there's one that's very similar to this. It's got A and a B. One you can use logic, the other one you could use the equation. Or you could use the equation for both. Doesn't matter. Yep. No. If you just logic it out quickly and do a little calculation, it's fine. Yep. I don't need an explanation. What do we have after 60 years for this particular isotope? Yep, James, what do you got? How'd you get that? Yep. Excellent. 2 half-lives, divide by 2 twice. You didn't even need to write that all down like that. You could have just put 3 grams. I would have said, yeah, good job. How many half-lives How many half-lives is 354 years? Yep. 11.8 half-lives. So to the exponent 11.8. And what do we got? Scientific notation or not, I don't care. Yep. 3.14 times 10 to the negative 3 grams. Nice use of the scientific notation. If you didn't, you'd have 0.003, right? That's 1, 2, 3. 14 grams. Okay? That's how much would be left. We don't like it? Or you like it? Like completely different? Like decimal way at the very back end? What do you get? 336? 336? We're liking 336 better? All right. I don't know what you did. 336. 336 for the same power of 10? 336. All right. Nolan, look at what you did to my video now. But that's okay. That's a 336 for those who are checking online and watching this sometime in the future. Okay. Only one question associated with it. All right. I think you were already assigned that question. It's just that either it's not in the video and it's not clear, or maybe it was, but it doesn't